Okay, dear friends of DigitalFUTURES, welcome back. Tonight, Chinese time, it's a great honor for us to invite two very special guests give the talks today. We invited Professor Mark Burry and Professor Mike Xie. I think both of them are the close friend of DigitalFUTURES. In the past few years, we invited Mike Xie, firstly coming to Shanghai, and who is right now, the guest professor of Tongji University. At the same time, he also engaged a lot to our PhD. Mark also joined us to the DigitalFUTURE PhD program. And actually, he taught last year in Shanghai and stayed here almost 1 week. So it's a very special experience. And it's a great honor for us to have this special two guests here. I would like to firstly make a brief introduction to you, introduce both of them. Firstly, Professor Mark Burry, who is the founding director of Swinburne University of Technologies, Smart City Research Institute. His role is to lead the development of the whole of the university research approach to meet the needs of all, including smart citizens for smart cities. Period is, he was a professor of urban futures at the University of Melbourne, 2004. Visual Information Architecture Laboratory, 2018. Mark was appointed as an officer of OA, Order of Australia, for distinguished service to spatial information architecture as an academic researcher and author, and an innovator in application of digital manufacturing and construction methods. 2018 also saw Mark elected fellow of ATSC, Australian Academy of Themes. First, putting theory into he in the to 1979 and to Mark has been helping strategies, especially those strategies coming from his later years, the implications of which only start becoming fully apparent as they're resolved for building purpose. So that goes to Mike Xie, Professor Mike Xie, who is also the fellow of ATSC, Australian Academy of Technological Sciences and Engineering, and who is also distinguished professor of RMIT University in Australia, and a guest professor of COP Tongji University. He used to be the head of civil engineering discipline at RMIT University between 2002 to 2012. He got a PhD in the University of Wales, Swansea University Kingdoms in 1991, supervised by Professor O.C. Zakinvich, FRS CBE. In 1992, he plays a leading role in the pioneering the ESO, Evolutionary Structure Optimization method. I think he will introduce this method to us tonight, which has been a far-reaching international impact on the structural optimization field. In 2011, he was elected as a fellow of ATSC. In 2015, he established Xie Technologies. He is currently leading an outstanding team to apply the ESO technology and other research outcomes he has achieved over many years to engineering practice, providing innovative, efficient, and economical structure design to customers, and realizing this design using 3D printings and other advanced manufacturing technologies. In 2016, He was awarded the AGM Michel Medal by the Institute of Engineers, Australian Distinguished Professorship. He won the Clunies Ross Innovation Award from Australian ATSE. In 2019, Professor Xie was awarded a member of OA, Order of Australia, for his significant service to higher education and to civil engineering. In the same year, he was awarded the highly prestigious Australian Research Council Laureate Fellowship. So that's a lot. It's maybe part of the introduction, because this two special guests is really important, really meaningful, and really influential globally. So it's a great honor for us to invite them to give us the talk tonight. So I think Mark would like to first say 15 by 15 minutes. Mark and Mike Xie, they will, both of them will give the lectures and have talks to each other. It's welcome. If you have any questions, you can just leave on the chat group. We would like to translate and put forward to both of them. So welcome, Mark. Would you like to start?
Thank you, Philip. And thank you, Philip and Neil, for yet another fantastic Digital Futures. No, nothing's going to stop you. Not a pandemic, that's for sure. And it's been going great so far. It's a great pleasure to be sharing the platform with Mike. We go back quite some time, and we've decided to look at something in common with Gaudí, where we collaborated on unraveling Gaudí's secrets. So I'm going to talk for a little bit and show some work about the Passion Facade, which is part of Gaudí's Sagrada Familia. And then Mike will pick up from where I leave off, and then I will pick up from when Mike leaves off, and then he will round it off. So without further ado, I will share my screen. Philip, can you just thumbs up if you can see that? Yep, it's sharing okay. So I've called this, it's about Gaudí, but learning from Gaudí, structural artist. Structural artist is a term that Michael Billington came up with when he wanted to give a name, generic sort of name to people like Isler and Mayan, the great engineers who had extreme aesthetic sensibility. And of course, that these people helped me understand Gaudí as someone who was absolutely in that space. So if we look at this one part of the building that we want to share, which is the Passion Facade. This isn't the first part of the building that Gaudí designed. It's in fact built entirely after he died, but he did leave a drawing which both Mike and I will talk about, I'm sure, from different perspectives. And it was given the task to bring this drawing to life. The bottom half had already been built and was completed in 1975. But first of all, I just wanted to remind everyone that what does it mean to be a structural artist, architect, engineer. So we're going to talk very briefly about the Colonia Güell chapel, which is this image here, what I think is the first architectural computer that I've come across. It's a 4-dimensional drawing. It's designed to register in tension all the forces of gravity that a building might present. So this is in fact the model for the little church that he'd been commissioned to do just outside Barcelona, hanging upside down, scale of 1 to 10 in plan, 1 to 1,000 in terms of, sorry, 1 to 10,000 in terms of volume and weight. So these little bags of lead were the digits, if you like, of the computer that Gaudí made. It took 8 years to make this model, and he was working on it nearly every week. These little discs you can see here had the calculations and the measured tension forces that had been taken from various parts of the building. He turned it upside down, photographed it, and that is the image of the building. Now, the reason I'm showing you this is because it is impossible to separate from Gaudí the architect, the constructor, the theorist, the philosopher, or the engineer. And by having this model on site, he was able to take measurements from it. It's an undrawable building because it's in 4D, but he was able to locate everything in space and build it. Well, build part of it. This is the crypt. It's only made of brick and stone. There's no concrete, there's no steel here. An absolute genius of construction, a genius of structure. He thought that in fact these pieces of stone, which are just been taken from the ground the way they are, were overstructured. So he asked for each one to have part cut away. And of course, the stonemasons who were asked to do this had no faith in the idea. So they forced Gaudí to stand underneath this while they did it, so that Gaudí was able to demonstrate he had absolute faith that it wouldn't fall down. But as you can see, it took 8 years to model the building, and then it took another 6 years to build just the crypt, by which time the client became ill and his children didn't want to spend any more of their father's money on this. So we don't have the completed building, but we do have a sense of where Gaudí could have gone if he hadn't had this interruption. When we look at Gaudí in a more general sense, we could take just one element, which would be the columns. And these columns for Gaudí reached their kind of zenith in his magnum opus, the Sagrada Familia, where he conceived the interior of the basilica as a great forest. And it's obviously a forest of tree trunks and columns and branches. But we can see from his very beginning that the column was something of a special architectural importance to him. This is the townhouse for his major client, Güell, who was also the client for the little chapel I just showed you, the one that never got finished. But what did get finished for him early in Gaudí's career, in 1889, he handed over this opulent residence, which is in the center of Barcelona as the Count's townhouse. And you can see already that Gaudí is experimenting with structure, he's experimenting with light and layers. So this line of columns has been split into three, and then you've got the windows sort of sticking out. Fascinating, but even more fascinating for me was exactly the same year he finished this building, which is the little church school for the Santa Teresian school for young women. And the budget was very low, very tight, which is why Gaudí had to make it a very rectilinear building. It's just like a big shoebox. And he effectively only used three materials. He used brick for all the structural parts, random rubble, which is just broken pieces of stone for parts which weren't taking any forces, and plaster of Paris, which we can see on the inside. So when you look at the plan of the building, you say, well, there's nothing much going on here. But in fact, it's an extraordinary achievement structurally when we start looking at this space I'm going to show you here, which is supporting three layers of masonry above it, only on single columns, single brick columns. So this is the space at the end of each of these floors, the first floor, and the entire structure of the two floors above are coming down on these single brick columns, which you can see here. It's a building of absolute modesty compared to the townhouse that he made for Güell. But look at the humor of Gaudí, absolutely making no effort whatsoever to pretend that these are anything other than single bricks. He's showing off. The column here has more than a purpose of referencing history at the Park Güell. These are actually pipes taking the water from the arena above down to the cistern, which is below. So this is a sustainable, Park Güell was meant to be a sustainable community of 60 houses. And this is the water supply, catching the water from above and taking it down to the tanks below. More interest, Gaudí is beginning to look into where forces really want to be. You can see this force diagram. This is a drawing by Gaudí himself, showing the columns here. He knew that a column doesn't necessarily want to be vertical. Most likely it wants to lean in to the forces. And of course, this is the principle that Gaudí took to the Sagrada Familia. He makes historical references back to the Erechtheum, where you can see the caryatid made out of random rubble. And of course, these columns, which I showed you here, made from just naturally occurring stone And there's that cut I showed you. His interest in nature, though, meant that he was actually fundamental in his research. He looked at the human skeleton with interest, and we can see this being played out for what became the design for the Passion Facade, a long project that went for many years. And that's what I'm going to just briefly take you through before. So the Passion Facade was proposed by Gaudí in a drawing. The drawing doesn't survive, but it was photographed. It was then taken up by his colleagues, his young amanuenses, which is Puigboada and Jordi Bonet Senior. So they were in their early 20s when Gaudí was at the end of his career at age 74, died in 1926. This drawing was then interpreted first by Jordi Bonet II, that's the son of Jordi Bonet, myself and Jane, from that original document, and then went on to be documented. And that process has gone on for decades and decades. We inherited the project after it had already been built in the bottom half. Very few people realized that, in fact, there was another bit missing, which is up here. So drawing on those bones that we knew Gaudí was interested in, that photograph of the skeleton came from his studio, and this very detailed photograph, we were able to get a sense of its spatial layout from the shadows. We had artistic direction through Subirax, the sculptor, and so we knew what we had to do in terms of representing the passion of Christ. That's the crucifixion of Christ, or the agony of Christ hanging naked from this horizontal cross. That agony had to be translated into the narthex, and we can see this coming out in the photograph of the drawing. But 17 years had gone into making a prototype of this before we had any digital tools. This is Jane scanning that original model. None of us are the new Gaudís. We're the agents of Gaudí who died. We're his successors. And so his thinking is taken through layers of people before us, and no doubt after us. So this model represents a lot of work, but it did not get where it needed to get to. If you look at that, it's not there. But by the time we came into the picture, which is about the year 2000, we could see that it was an opportunity to think of Gaudí's last experiments in hyperbolic shapes. That's the hyperboloid revolution and the hyperbolic paraboloid. Could we combine them in a way that he himself would have had great difficulty to do, whereby the straight edge of the hyperbolic paraboloid could intersect with the straight lines on the hyperboloid behind it? No time to give you a geometry lesson, but the point here is that as designers, we don't want P1, P2, and P3 simply to be where this hyperbolic paraboloid happens to intersect with this hyperboloid. We want to be able to design parametrically this such that we can have 4 of these hyperbolic paraboloids intersecting cleanly with the hyperboloid, the blue surface, with another 4 at the top, with nothing clashing. And this is a remarkable challenge. This is effectively the only drawing that matters. It's the schema which went to the mathematicians and the programs that helped us develop the tool to build the parametric version of this. Here you can see an early experiment when Rhino has just appeared on the scene. We were able to start looking at scripting within Rhino. We were the first people to adopt 3D printing. We know this because the company that invented 3D printing said that we were the first architectural project to involve it. Imagine trying to make this by hand as a trial model. This is Jane's parametric model. Jane modeled the entire facade as one single parametric entity. In theory, you can't alter a single dimension on this model without it having a ripple-on effect. It's more subtle. I hope it looks subtle, but it's even more subtle than it looks. In plan, it's actually a parabola from above. All these columns are leaning at different angles from each other, both towards the center of the building and towards the center of the facade. These hexagons here are rippling up. They're actually changing size. The one at the top is 10% bigger than the one smaller, and so there's a gradation. At the same time, maintaining every single hexagon edge is touching the next one. We didn't have the computer power to, or the ability to scan the building when we did this in 2000 and 2002 to 2008 was the main design period. At that time, we didn't have, we couldn't scan buildings, so we had to do this without ever being able to place it. But we had very strict criteria, like this window, which is in the middle of the facade, had to be seen in its entirety through the, this is the window here, through that. Sorry, I've just got my timer telling me to shut up. Just almost there. We prototyped in 3D, that's in polystyrene, then covered in glass fiber to look like the piece. And this was located there. And you can see it coming up. It's a parametric physical model, one-to-one. We were busy moving this backwards and forwards to see if we can get the shadow in the right place. Now, this bit is where I sort of segue into Mike's account, because exactly at the time that we were interpreting this drawing, and you can see this emerging here as the version that makes use of these geometries that Gaudí so loved at the end of his career. We had no idea what the structural story is behind this. But Mike came in on the scene, and I'm going to hand over to him now, and he'll pick up. I suspect you're going to see some of these images again, but you've just had an architectural interpretation of them, and now you'll get the engineer's view.
Let me share my screen. Yeah. Can you see my screen, Mark? Yeah.
Yes, yes, it's good. Yep.
So in 2004, it was the first time I worked with any architect, and Mark showed me this picture of the Passion facade. And also, oh, sorry. Can you hear me? Can you hear me?
Yes, yes.
Okay. And apart from this, and Mark showed me several hanging models of Gaudí, and I was working on, at that time, mainly on aircraft structures and try to reduce the weight of the motor vehicles and aircraft. And I was astonished to see some of the pictures which I've previously seen in my work on engineering structures. And, we proposed a simple method for finding structure forms called Evolutionary Structure Optimization in 1992. And the idea is actually very simple. If you want to design a better structure, you can actually start from any shape and do some assessment of which part of the structure is inefficient or unnecessary. So you can chip away those inefficient material to get a better design. And while I was preparing this slide this morning, it occurred to me that this process is actually just like what the sculptors do. They can start from a block of marble, and by chipping away all the unnecessary parts from the block, and what's left over is it would be a much better design or a beautiful statue like this. So the ESO concept has been used for thousands of years by not only engineers and also architects, sculptors. And what we have done is to try to use this concept for engineering designs. When you look at the hanging models, these hanging models are in these chains are in tension. So if you want to find a form which is suitable for tensile material like the steel chains, you can start from any shape, and by removing the material which has the highest compressive stress, you would find a shape which would be suitable for the tensile material. So I show you a simple example of how this works. So you can start from a full design and apply the boundary conditions and apply the forces. And in order to find a shape which is suitable for tension, you can, every step you remove the areas with the highest compressive stress. And what's left behind is a shape which is in pure tension. So that would be suitable for materials like fabric, membrane, or cables. And when we are dealing with Gaudí's designs, everything is made of stone. So it's the structure would be most suitable for compression, like an arch here. So in this kind of structure, everywhere would be in compression. And for a simple boundary conditions, you would know it's a simple arch. But if the boundary conditions is more complex, it's not that easy to find a suitable form. But using our evolutionary structure optimization method, you can actually find a shape which is subject to any boundary conditions or forces. So all you need to do is you start from a full design domain and gradually remove the material with the highest tensile stress. Then you would get a shape which would be suitable for compression. That's how we started to explore the shapes proposed by Gaudí and designed by Mark and Jen for the Passion Facade. So our starting point is that photo Mark showed me. This is the original proposal from Gaudí. And from that, we can draw up a design domain. So this is an engineering drawing by one of our collaborators, Peter. And from this, we can apply the forces and gradually remove the areas in tension so that resulting shape would be suitable for compression and for the stones. So this is the fine element model for the engineering drawing for the initial design. This is the front and the back. By gradually removing the point with the highest tensile stress, we would immediately see this process, and soon we will get a shape which bears a lot of resemblance to what Gaudí proposed for the Passion Facade. So when we saw this image, we were actually very excited. And at that time, I think it was around 2004. And I go to see Mark and Jen every Monday morning and to exchange our results. It was a very enjoyable and exciting time. And this is one of the models we found from by simply applying the evolutionary structure optimization technique of removing the tensile material. And you can see a lot of similarities from our rule-based outcome and what Gaudí and Mark and Jen designed for the Passion Facade. And we actually done a lot of work on this. Some of the results we have never shown to the public. At one stage, we were thinking about if we were to build this church in Shanghai, it would be a totally different shape because in Barcelona and Shanghai, the earthquake loading would be completely different. And in Shanghai, there's much higher seismic forces. If we apply those high lateral forces from earthquake, we would actually get a quite different Passion Facade like this. So with lateral loading from earthquake, our algorithm would naturally generate those cross bracings to resist the earthquake loading more effectively. And we also look at the, I think around 2005, Mark was looking at these columns on the slope. So we were using the ESO method to see what kind of shape we would get by removing those areas in compression. So on the left-hand side is what we have got from the ESO process. So we can actually run our software and get this result within 5 to 10 seconds. And what was astonishing was if you compare our ESO result to the actual columns on the passion facade, they're almost identical, which got us really excited about this, what we found. We are using totally different tools from what Gaudí did. So we are using computer simulation. We're using a rule-based algorithm to obtain this shape. And Gaudí was using those hanging models and also what he observed in nature and what Mark has been working on using parametric designs. But no matter what tools we have each used, but our design objectives were the same. We want to design a shape which is most suitable for the stone type of material, which would be suitable for tension. And we want to use find a shape which is structurally most effective or efficient. So we use different tools to arrive at the same design objective. So it's not a pure coincidence. We are aiming to achieve the same goal through different tools. And this is the research we have done for finding two columns on a flat surface. So starting from this initial design without any bias, we asked the computer to remove the areas with the highest tensile stress, and within 10 or 20 minutes, we will be able to find these tree branches. And if you compare our ESO result with what Gaudí has done inside the Sagrada Familia church, you can see a lot of similarities between the structure-based optimization result and the design by Gaudí. So that was a method of removing the inefficient material. And a few years later, we improved our technique by allowing material to be added to the most needed locations. So these days, there's a lot of hype about additive manufacturing. And when we look at these algorithms, it's actually a combination of additive and subtractive processes. So not only do we remove the inefficient material from the structure, we can relocate these material to the most needed parts. So in doing so, we can make the algorithm far more robust and efficient. So I'm going to show you one simple example of using this bi-directional evolutionary process. So this is an example of design a bridge. So you apply the boundary conditions, so fix the 4 points at the bottom, apply a gap in the middle, because it's a bridge, you need to leave some space for the vehicles to go through. We have a non-designed deck, and all the rest we can let the computer to generate. So initial design can be very simple. So we can have a slab with 4 columns. This is also a bridge, but it's not a best design. Doesn't matter, starting from this humble beginning, we can let the computer to decide where to add the material and where to remove material. So if you look at this process, so we're not making minor local modifications of the initial design. We are making fundamental changes to the structure concept. What we're getting is from a beam and 4 columns, we obtain an arch. And on this arch, we have those additional tree branch type of structure to make the whole bridge to be evenly loaded. So if you're looking at this kind of arch and those tree branches, it echoes clearly what Gaudí did in many of his designs. And we run several workshops with students, and last year we did a workshop in Tongji, and in October, Mark and I were in Barcelona for exhibition. Our workshop were closely related to Gaudí's structures. This was done with two of my students, Nick Bao and Xing Yan. So this would be on the left-hand side, the initial design, and using our BESO technique, we will be able to find those structures very similar to what Gaudí designed inside Sagrada Familia Basilica. So this is a 2D version of what we can find from applying the BESO technique. Again, these columns, and they're not always vertical. A lot of the columns are at an angle. And these are the 3D version from the initial design, which is very ugly block. From these, by applying the loads and removing the inefficient parts, we will be able to find these kind of designs very similar to what Gaudí proposed. So these are the one of the pavilions we did last year in Tongji University. We designed these columns following one of Mark's paper. So these are not circular columns. And in Barcelona, we made a further enhancement to our design. So the roof is now curved. So from this, because it's symmetrical about two planes, so we can simply analyze a quarter of the model. So apply the boundary, fix at the bottom, apply the loads on the roof, and then our BESO technique would start to evolve those inefficient material to get a design. This is a quarter of the pavilion. And this would be the full pavilion for the curved roof. It was quite heavy, so we only printed 1/4 of the pavilion, and we exhibited in Barcelona last October. So now I'll hand back to Mark for some further comments about Gaudí's work. I need
oops. I'm back. Are you seeing this full size or is it small? Is that full size? Before, when I was practicing, some of my images were coming across as too small. Does this seem the right size?
Yep.
I assume it is. So thanks, Mike. We talked about the architecture and the engineering behind this project, but one of the distinguishing features of the Sagrada Familia is that the entire project is one team. So the engineers, the architects, the builders, the people doing the costing, the managers are all in the same team, which means that we make decisions as a team. So the rest of my my talk is just to talk about the way you actually make the building. So it's one thing to do the structural design, it's another to do the formal design, but making it is also as an incredibly important part of the project. This is Jordi Barbagne, who's a stonemason from just north of Barcelona, third generation. He's a sculptor, actually. That's his first thing he would say he is. He's also a stonemason, but and on top of that, brilliant with technology. In this case, we're looking at our proposal for the top of the column. It's extraordinary, isn't it, that Mike's software and Gaudí's mind came to a similar conclusion. None of the columns in the Sagrada Familia are vertical. They're all at an angle. Some of the angles are quite pronounced, but some of them are subtle. But here we can see our discussion between Gaudí Bavin and myself about the nature of these hyperbolic paraboloids. We wanted to make them as thin as possible, to make them sharp and again, sort of represent the tension of the Christ's crucifixion. But he's pointing out that yes, he can make these, but do I think that a piece of stone weighing several tons would survive having these very delicate surfaces? So he was actually reminding us that the brutal process of making sometimes forces us to limit our aspirations. The column is something that emerges from the computer, but it's 9.5 meters high. How exactly will it be made? Working with Gaudí Bavin, we first of all looked at simulating whether a diamond wire could move through space and cut this. This is the most difficult part of the column. And because Gaudí is using these ruled surfaces, you can see that the same geometry allows a wire, if it can move in space, to cut nearly all of this, just this tiny little bit here left by hand. But meanwhile, Gaudí Bavin is looking at other technologies and techniques. One of his ideas was to use the saw so that we could get a different kind of texture. I love the fact that parametric modeling extends to designing the piece of stone from which you're going to make pieces. You don't just take half the mountain with you now, you just take the smallest piece possible. We've got this giant saw cutting the stone to be the minimum we need to make the columns. Here are the columns here. The diamond wire has been used to take as much of the stone away as possible, leaving the minimum for the robot. And I'm not sure that anybody would be able to say that they had a 7-axis production going on for stone before Gaudí Bavin did in 2000. This is a 5-axis robot which he acquired from the auto industry at a time when nobody was bringing robots into construction. And then there's this 2-axis turntable. It's a turntable which rises. So he's got 7 axes of movement there, looking at the most difficult part. And that's just a prototype. And then in the life of the project, whereas we thought we would actually need to have 5 elements to make one column, he found that we could get this 9.5 meter high column reduced to 3 elements with this 6.5 meter long piece in the middle. It's actually extraordinary. He has to turn the stone and re-register it. All this technology is the technology that he came up with. He didn't hand this over to some specialists. It's something that he does himself. And the stone itself at its narrowest is 35 centimeters. And one time he told me that he thought it was most unlikely you could make this piece of stone by hand, as it would probably break just from the violence of hitting it, hammers and chisels. But I always point out that these robots don't eliminate the need for humans. It's a augmentation of human effort, not a replacement in the case of stone. And nor does the model disappear, just because this is effectively a file to factory process where we can go from the computer to the robot without involving humans. That's not quite the case. And Gaudí Bavin always wanted a 1:10 scale model so that he could explain what was required to the people making these complicated pieces of masonry each day. And even with mechanical tools like this core bit drill is sculpting out, because although it doesn't have the same seismic conditions as Shanghai, nevertheless we have to design the Sagrada Familia for a 7.5 Richter event. So although this is completely a compressive structure, the entire facade that I've shown you is stone on stone, there are these 1 elements of concrete which go in horizontally along those hexagonal prisms. And each one of these takes 3/4 of an hour to cut. And you can see how many of them there are to cut. And there are 36 of these, top and bottom. So that's the sad truth. We can say that the robot has made the stone cheaper, but we can't say that it's made it cheap yet. It's certainly a little bit quicker. And then you can see the column as it emerged. That's the first one. That's Tony Caminal, the technical architect in charge of stone. He's 1.85 meters in height. And you can see just how big the column is. And that piece there was made as a single piece. Now, the other interesting part of the story is just the precision. If you're still awake, I know it's only early evening, but still, if you're awake, you'll see that it's starting from the end and working its way towards the center. And as architects, we thought the logical thing to do if we were builders would be to start in the center and move it out just in case it wasn't quite, dimensionally perfect. But by using these surfaces, there is actually no dimensional constraint. It is perfect. And they were able to bring this, the colonnade up. You can see that there's the parabola that it sits in plan. And here you can see each of these hyperbolic paraboloids are kissing each other, exactly touching, and no more, no less. And I'll just finish up with some rapid pictures of it all coming together. I like this one because when you see people on top of it, you realize these, what look like very small elements when you're seeing it from the ground, are actually large. They're almost the same height as a person. You can see it emerging from here. Starting from the edges, working towards the center. There's obviously no opportunity to shave this or adjust it. It has to be a perfect match. And just the last few slides on this. Here we are. The last challenge for us from Mr. Bonnet, the former director, was that standing where this photograph was taken, you needed to be able to see the oval, the elliptical window that's sitting on this plane, the plane of the towers, without having any of the columns in front of it. And we had to do all this by calculation because there was no opportunity. We did not have a model of the facade behind with which we could actually check how things were going. There's Jane. And then you just see the precision. That's why there's no problem. If you use geometry, you can have the geometry hidden. It's not calling out to you that this is a hyperbolic paraboloid and these are hyperboloids for columns. It's hidden, but very, very effective for allowing the job to be done. Here's the Christ's tomb, which is hidden at the back of the facade. You can see the facade there just coming to conclusion. There was this drawing, which is the only way that we could demonstrate to Senor Bonnet that this ellipse here was going to be visible without being occluded by these columns. There's the drawing, and there's the completed facade, and there you can see the ellipse without any problem. The color is different because this was the only stone that we could get that had the same strength as the original Montjuic sandstone, but this sandstone is not available. And we have never found a rival source for it. It's actually from Barcelona, but it's a national park and cannot be quarried. The towers, which are nearing completion in the center of the building, are being built from granite, which has a close match to the color. But this, at the time, we could only get the gray tarn granite. Now this, as you know, we talked about these objects here. They're almost a human tall. These are 9.5 meters tall. There's no steel, there's no reinforcement apart from horizontally. It's a compressive structure that Gaudí was able to register in a drawing and that we were later to find out was perfectly adequate for the task, as you can see, is now completed. So I'm going to hand back to Mike.
Can you see my screen, Mark?
Yes, it's good. Yep.
Okay. When I go to conferences in the past 20 years, people always ask me, when you use a topology optimization technique, can you guarantee your solution is unique? And can you guarantee it's the best or it's the global optimum? Because these questions are very important to mathematicians. They want to ensure that your algorithm is perfect and to generate the absolute best solution. But the more I work with architects, the more I've been asked the opposite question. And the designers, they don't want to have a single unique solution. And they would prefer many different design options to choose from. So this is a topic I want to spend 10 or 15 minutes on. So if you want a global optimum, this is an example you can have. So Mount Everest has it's the tallest mountain. It's unique. It's definitely global optimum. But sometimes this may not be what you want as a designer. Perhaps we are more interested in something different like this. And some of you may have been to this place in Zhangjiajie in China. So these mountains, they have many different peaks. And you can see these peaks are of similar heights, but they have many different forms and different views. So if we talk about those design algorithms, we want to generate many different design options like all these peaks. The height could be something like a structure performance, and the shape could be the structure forms we are looking for. So that's what we are trying to do, different from what mathematicians try to achieve. So we want to create many different options, so diverse designs, but all these designs are efficient designs without changing the loading of boundary conditions. So I would refer you to an interesting example from Philip Yuan. He has been designing these bridges for Digital Future every year. I'm sure some of you have seen Philip's bridge. But there's some conditions we would never change. It's always in this place, so the boundary condition would not change. And the loading would not change either. Every year you will see Mark and a few familiar faces, Philip Bloch, Philip Yuan, Matthias. And so if we don't change the loading condition, boundary condition, how can we design a different bridge every year? So this form actually was found using our BESO plugin Amoeba, but it doesn't mean that we can't use Amoeba to find a different form. So there are several strategies we have developed in recent years to find diverse and competitive designs. There's many tactics. The simplest one is what we often do when we use a rule-based design. We can change some of the parameters in the optimization algorithm. Say in topology optimization, there's one algorithm, one parameter we can use. So for this simple example, you will see this kind of movie. But even for this very simple case, this is not the only design. What we can do, we can sacrifice 1 or 2% of the structure performance, and suddenly we would have many different forms. So here, the only thing we did is to change a parameter called filter radius. This filter radius would control the size of the minimum member. So if we use a smaller filter radius, you will have many details with smaller members. When you compare these 5 shapes, they look quite different. But in terms of structure performance, they're almost the same. The difference is 1.4%. So suddenly you can present to your client with 5 different design options, but each of them has very high structure performance. And the second tactic we have developed is to penalize what's already exist. I show you one example here. So this is a Qatar Convention Center designed by Arata Isozaki using extended ESO method, which is very similar to BESO algorithm. So if we run this example using our BESO code, we can find it very quickly. So the model is simple. You fix the two bottom points, apply the uniformly distributed load. Using our BESO code, we can get the shape over a cup of coffee. So 10 minutes or 15 minutes, you would get this shape. So this is what we can get using our BESO's code. And they're very similar to what Isozaki did for the Qatar Convention Center. But this structure has already been built, so no one wants to build this same form again in another city. You can't plagiarize a famous design like this. But we can still use the same BESO technique to find other forms which satisfy exactly the same boundary condition and the loading condition. All we need to do is to provide some penalty to what is already there. So this is the existing form. So all the material in this shape, we would apply a penalty. Depending on how severe your penalty is on the existing form, you can get many different other shapes. So this is another shape we obtain using BESO technique by having some penalty to the existing material. You can see there's an additional truss in the middle and other parts look different. So all the details look different from the existing design. And if you compare their structure performance, they're different slightly by 10%. But 10% or even 20%, it's not significant because when you deal with any real structure, there are many other factors you need to consider. And structure performance is only one of many factors. So there's no need to achieve 100% structure performance when you have so many other factors to consider. This is another example of having a bridge, but this time the deck of the bridge is in the middle. So if we only consider structure performance, you will get a design like this. But next time, say you want to design a different, another bridge, instead of building a same bridge, you can apply a penalty to the form in this existing design and to get the second one. So by penalizing the existing form, we can get a second design like this. If you compare this to the first one, which consider the 100% structure performance, we have two parallel arches. And if we penalize this first design, the two arches are getting closer. So the two arches become one. And then you can do the third and fourth design by penalizing all the previous designs. So you run the next one by penalizing all the materials appeared in the first two, and then you can get the third one. Because if you look at the third one, now the two arches becomes almost one. So you now have three design options that look quite different, and then the traffic flow would differ as well from in the three bridges. But in terms of structure performance, they're almost the same. They only differ by 3%. So all these options, although they look quite different, you can always guarantee to your client or to your collaborative architect that they are all very good in terms of structure performance. But then you have so many other options for your client. And next one is we can use some of the constraints as a design driver. So quite often the constraints are something we need to avoid. But in design, we could use the design as a positive attribute to drive design in different directions. So this is one example of design a bridge type of structure. In the top model, we can have material everywhere. In the lower one, we say we create a gap in the middle. So this is a geometric constraint we applied to the lower model. If we run the ESO for these two models, we will see quite different evolutionary process. So the top one allows you to put material everywhere. The bottom, it says you should leave a gap in the middle. We got two totally different designs. And if you compare the structure performance, they're close. The difference is 14%. So the lower design has a structure performance 14% worse off compared to the top. You may say that the upper one is a better design, but it may not be true, because if you're talking about design a bridge, the top design is not, it doesn't even look like a bridge. It's more like a stool or a bench. And so there's other architectural requirements we need to meet quite often. So although the structure performance seems to be worse off, but the lower design is actually more like a bridge. And this is another example of using constraint as a design driver. Sometimes you have certain parts of the building you can't touch, or say you have certain features you want to, the architect may have prescribed, or you are doing renovation to an existing building, certain parts you can't remove. So all these could become a non-design area, and the evolutionary process would design by not touching these fixed design area called non-design domain. So we have 4 different designs, and they all look different, but the structure performance are very close. They differ by only 7%. The other way is you can penalize part of the structure. Say for this long cantilever, you would get a symmetrical design like the one shown on top right. But sometimes you may want to have a non-symmetrical design or some other features, so we can penalize the lower half of this design domain, say the lower half using a different, weaker material to build. And in doing so, we get 2 different designs. And the 3 designs look quite different, but their structure performance are actually very similar as well. The other technique we come up with is we can introduce some randomness. So we can, in the design domain, we can randomly dig some holes. And these holes are there to try to change the evolutionary direction. So these holes can be filled later on, although they're initially there. By having these random holes, every time you will get a different design. It doesn't mean that you are getting the wrong solution. So although the 2 shapes look totally different, but their structure performance are both very good. So the top one is 100% good in terms of structure performance. The next one, it's unsymmetrical, it's quite different, but it's 98% of the best performance you can achieve for the structure stiffness. So we used our technique and applied to many different structures, and I show you quickly a few examples we tried. So these are some of the footbridges we designed. So this is one we designed for Melbourne. And so we actually made a mock-up 1:4 scale model using those reusable mode. So 6 identical pieces, we can connect them together to make such a bridge structure. This is another bridge proposal we did 6 months ago for a client in China. So this is another view. And that's a proposal we did for Suzhou sometimes back. And the BESO technique, it can be used for many other applications. So, so these are some of the examples my students have done for different applications using our Amoeba software. So these are the tables in my office my student made for me. And this last year when we were running Digital Futures in Tongji University, we have some undergraduate students, 2 girls, they designed some high heel shoes for themselves and using Amoeba and 3D printing. This is done by another student in last year's Digital Future workshop. A pavilion, a wooden pavilion obtained using our Amoeba software. So this is a unmanned aircraft. So we have, initially we have material everywhere, and using BESO technique, we can remove all the unnecessary or inefficient material. We can 3D print the whole airframe in one piece and add on all these bits and pieces we can get from eBay, and it can fly very well. The Amoeba software we have developed, it's now getting quite popular among architects and engineers. So it's a Rhino Grasshopper based plugin, and all the computing is done on the cloud. So we have one server in China, another server in the US. So that those cloud computing allow the very efficient computation to be done. So these are some of the examples using our Amoeba BESO plugin. And I show you quickly some of the examples. And this week, we have a group of very talented students. So these are one of the projects done by the current students. After learning the Amoeba software for a few days, they're redesigning this Eiffel Tower, which is, I found this very interesting. And to me, the old Eiffel Tower, it's the product of Industry 1.0. It was built at the end of the 19th century, so it's more than 100 years ago. Now we're talking about Industry 4.0, and with the new technologies, not only for digital design, but also for advanced manufacturing, we would be able to make this tower much lighter and in a totally different form than those rectilinear forms designed by Eiffel more than 100 years ago. This is another project by the current students, a pavilion with all the tables and the chairs, all designed using Amoeba software. And this is another group. So I'm giving you a preview of what we are going to present this Saturday for the Digital Future workshops. And I give you the last slide to end my talk. So this is a project of Philip Yuan's team, and we are very lucky to work with his team to design 40 tree branch type of columns in these 2 buildings. 40 columns like these trees. When you look at these tree branch type of columns, I'm sure it will remind you what Gaudí did for many of his projects. Although Gaudí was living almost 100 years ago. But you can see from these pictures and many other projects around the world to see the enormous impact Gaudí is having in many corners of the world, including Shanghai and many other parts of China. Thank you.
Hi, is Mike here?
Yep.
Yes. How about Mark? So would you like to kick off the discussion part? Hi, Mark. Can you hear me?
Yes. Yeah. I just maybe Mike could stop sharing the screen.
Yes, I invite the postdoctor Wang Xiang also join us in the discussion. Yes, he's also a specialist in the structure performance-based design. So I have a question first name, maybe want to ask both of you, Mike and Mark, because I think the formation for the Sagrada Familia actually is totally different between Gaudí and Mike Xie. So could you, Mark, could you analyze this kind of graphic static hanging process by Gaudí? What's the difference between the Gaudí formation process and Mike Xie's formation process? It seems to me, what Mike mentioned, the ESO formation is like a black box, a structure performance-based intelligence design process, while I think Gaudí actually is designing a quite physical hanging machine. That is maybe the first computational engineering process before the computer coming to the design process. So can you tell us something about the difference between Gaudí and Mike Xie's ESO algorithm? Is there any difference between them? Mark, questions go to the architect.
Okay. Yeah, just raise your hand if I talk for too long, because that's a great question. But one of the unfortunate characterizations of the difference between the architect and the engineer is that the engineer solves problems and the architect seeks solutions. Seeks options. So in other words, the engineer drills down to the answer, whereas the architect blossoms and branches out to multiple answers and then uses competing criteria to select which is the one they'll go with. What's beautiful about Mike's work is, I'm answering your question, by the way, but I'm approaching it a different way. Mike's work shows that intuition, an aesthetic eye, all these things, prior knowledge, are still at the front. You don't have BESO or ESO drilling down to the single answer. With Gaudí, obviously, there's more to him than meets the eye. With the hanging model, that was a scale model, empirically registering the forces of gravity and tension, inverting it and saying, there you are, there's the optimized structure for in compression. But it wasn't like, here's the plan, therefore the church must be this shape. He knew that if he put loading eccentrically to the model would be pulled into a different configuration. And that's what the towers do. Every time he wanted some change, he would either reduce mass by putting a big opening or add mass by adding a tower. I think that's the same as Mike Xie's BESO. It's just that it's empirically done by hand, but the instinct is coming from the mind, and that's no different from anybody applying the software. With the Sagrada Familia, a lot of people think because the hanging model was currently located in the museum at the Sagrada Familia, that Gaudí used the hanging model for the Sagrada Familia. He didn't. He couldn't. He had to take the existing design for the building. He wasn't the first architect, he was the second architect. And it was already being built in a classical, well, a neo-Gothic plan. And obviously, if you can imagine a typical neo-Gothic cathedral, if you tried to do it using the BESO method or the hanging model method, it's not going to be tall vertical columns and vertical bays. It's going to be pulled out of shape. Well, he couldn't use that method for that reason. What he could do was use calculation. And in my workshop, which we're running with Sharan earlier this week, I did show the students the calculations that were done for the Sagrada Familia. He used the static analysis for it. You saw a hint of that with that section I briefly showed at Park Güell with the reclining columns. So I think the black box side of it is an unfortunate. It's unfortunate if it's in the wrong hands, but if it's in the hands of someone like Mike, it's a means to an end. And I don't think there's any difference between Mike with his black box computer and Gaudí with his strings and the weights. Intuition has to be at the front end of the decision making.
Yes.
I would like to add a comment to Philip's question. I think one of the reasons ISO and BESO technique have become popular among many architects, it's because although it is another black box, but this black box is much easier than most other black boxes in the similar field, because we are using very simple rules. And when you see the structure evolving on the screen, most students can understand why it's moving in a certain direction. So our algorithm is based on very simple rules, and most architects can understand. The second comment I want to add is people, I think, what Gaudí's method and the ISO and BESO method are quite totally different. But to me, I think to some extent, we are automating or computerizing what Gaudí is trying to achieve in the physical model. So instead of spending 9 months to build a hanging model, we can achieve same goal through the automated process of computing.
Good. And a second question goes to the design relationship between the human being with the fabrication process. I think in Gaudí's time, it's quite interesting from the hanging model, how to transfer it to this kind of hyperbolic surface formation process, because we can find a lot of this kind of details. It looks like a handmade process, but it adding a lot of quality details and engage into the final the church column and the beam, everything, the whole system. But the question goes to the machine making age, including Mark actually is the first architect to implement this kind of robotics in the stone cutting in the history. Do you think if this kind of intelligent machine engage into the design and construction process, a lot of this kind of details or the quality of the thinking process is lost by this kind of machinic process, because everything is very well could be designed, could be predict on the paper in the computer, but actually no traffic, nothing unpredictable in the construction process. But while we take a look at the original Gaudí's construction, we can see a lot of details like the small stone, which is not cutting edge, or something maybe missing part of it, but still it's a column is support there. this kind of handmade craftsmanship which engage into the construction process. So a lot of people talk to me, including my student, when they visit Sagrada Familia. They talk to me the original handmade church by Gaudí gave a very good quality by the human hands. But while the simulation, optimization, and the robotic fabrication engage, maybe this kind of craftsmanship is too well done, probably. So the second question still goes to Mark. Do you think this kind of machinic process actually lose a lot of this kind of creative or this kind of quality of the craftsmanship of human being? Do you think anything missing in this kind of process?
Yeah, well, the answer is yes, potentially yes. But I would say to anybody who hasn't been to the Sagrada Familia yet, when you go into the interior, one of those columns is not made by the robot. It was made in the 1950s, I think, by hand. So we know that the column that Gaudí designed is possible to make by hand. And I would love people to say if they could find which one was made by the machine and which was one was made by hand. I think a question that I've always had is the so what question. If today we could take one of Mike's BESO objects and just press enter on the computer and a robot can make it, there is no need for any geometry. All it needs to do is translate what has been described as the most efficient outcome through BESO. So I've had to, over the years, justify, well, why are you so obsessed with these hyperbolic geometries if we don't need them anymore? After all, we can make anything. And my answer is that if you did just translate the machine design to the machine making without any part of the, I don't think the hands have got anything to do with it. I think it's much deeper than that. I think it is the intellect. And what I at pains to point out in those columns for the Passion Facade, actually we didn't need to use the hyperbolic geometries because we could have just made them through a kind of a rationalized shape, and the robot could have made them anyway. Except I'm certain that there is a pleasure that you get from the use of these geometries without knowing that the geometries are there. It's something, because it's a coherence. And anyway, we know that if the whole building was to be built like Gaudí had made the Nativity facade, it would never have been finished. It would have been abandoned. It took him 43 years to build one facade and part of the back wall. Right? It's not very viable. So we do have to use machines. And one last point, think of those brick columns that I showed you, the single bricks. You can't get simpler than that. It doesn't matter whether they were laid by a machine or by hand. Their interest is intellectual. It is the fact that he knew that those single brick columns, they couldn't be any smaller than that, were going to be able to hold up 2 floors of masonry, no timber, all brick above it. So I think it's about in whose hands are these tools. And if you've got sensibility, it shouldn't matter whether you're using the machine to cut corners in terms of time and budget. There should be an intellectual engagement that transcends it.
Good.
Which is why Gaudí is important to us, because he gives voice to that.
Mm-hmm. Good. Okay.
Sorry.
Wang Xiang, would you like to put forward some questions? Yeah.
Okay. Hello, Mike. Hello, Mark. And it's a great honor to be here to discuss with you. And first, I want to ask a question because I think your collaboration is very inspiring for us. The architects collaborate with the engineers to use some new computational tools to create some new things, really cool things. So could you tell us some stories of your collaboration, how you organize that? Because we have also collaborated very a lot with Professor Mike Shear's team, and we have tried many ways to communicate and create some designs. So what's your story? Could you tell us some things about that?
I go first, Mark. I think I'm most fortunate to have met Mark. I think it was toward around 2000, and before that I hardly knew any architect. I was totally new to this field, and Mark was very generous in supporting me for so many years and introducing me to many other experts in the field. So gradually I was able to do some work and getting to know more about architecture. So I'm very grateful to what Mark has been doing and to support me to get me this far.
Well, I could say exactly the same. What I'd like to refer to as in terms of stories, is my education as an architect at the University of Cambridge. And we were not maybe, 30 meters away from the School of Engineering. And we went there once. In 5 years of study, we went to the engineering school once, and that was to break things, because they had machines that could break things. We could do stuff in concrete and then take it over there and see how concrete breaks, full stop. And although there are splendid exceptions, the fact is schools of architecture and schools of engineering typically do not have much to do with each other. So the story, which the question you asked could be put the other way, which is, do you think there's enough relationship between architects and engineers? In the Anglo-Saxon world, at least, we have two different professional bodies. The engineer gets accredited by the Engineers of Australia, and the architects of Australia. My fascination for having met Mike was at last finding someone that I could understand in terms of what the engineer's craft is. I don't need to know the mathematics because it wouldn't work, but I could see a creative conversation. I look forward to the day when architects and engineering, it's the same study. You just have people who are more interested in the numbers, and some other people who are more interested in the theory or the history. But to have this parallel study, I don't know what it's like in countries like China, but I imagine that there aren't many architects who are also engineers. I think we have to collaborate, but it would be better as we see software like Amoeba being taken up by architects. I mean, architects are hungry for that opportunity to engage with the forces that their buildings are meant to be accommodating. They don't want to just hand it over to a specialist. So I think Mike and my story is that we had a mutual interest in intellectually understanding each other's contribution to the built world.
That's a great.
Yes, and yeah, Philip, please. Okay, I'm very impressed by the every time Professor Mike's presentation to us. He can present the background theory very simple with very good examples for us. I like the expression from him. He showed us the process of like amoeba, like the topological optimization as something like sculpting. Because I think as architects, we what the great engineers and architects like Gaudí, they have given us is the new ways to think how we can create structures. Like as Gaudí, we mentioned, we always thinking of the reverse hanging technique. So he used these simple ways to give us, and then we can have a method to design structures. And we also have like Isla, he has some thing like inflating and create structures with pillows, something like that. And we also have today the method as sculpting, like we can have a rough structure and then let the computer to calculate for us. So I think this is the interesting way as what I have thought. I still have a question to Professor Mike, and I am wondering about what's your opinion about the differences between the topological optimization like Amoeba has done and the method of the graphic statics, because when we talk about Gaudí, I think the method he has used is something like that, and today you have new ways to explain Gaudí in the new method. So what's the your opinion about this?
I think static graphics was very popular probably 100 years ago, and at that time there was no computer, and so it relies on hand calculations. So to me, honestly, I don't think with the current development of finite element method, there's very more general tools. We still have to go back 100 years using those old tools. That's my only personal opinion. I strongly feel that we have much more powerful tools these days than graphic statics. We can use, because there's still a lot of limitations on what you can do with graphic statics. Even 2D problems, it's not easy to solve. In 3D, it's almost impossible, or it can only solve very simple cases. But with finite element analysis, there's no such limitation anymore. So I think we should move with the development of the analysis tools. And I don't think we have to still stick to those popular tools which was used by the engineers 100 years ago.
Yeah, that's actually, I want to add something. Can you hear me?
Yeah.
Yeah.
Yes. I want to add something to the discussion on that, because in the past 3-4 years, we have made a lot of discussion on the graphic statics and filament element design. Two kinds of totally different structure, performance-based design methodology. So that's why I set up collaboration with Mike's technology. And at the same time, I also looking for the developer, the software developer, Philippe Bach. Actually, Mike introduced Philippe to me, and I very quick looking into the secret of the computing graphic statics, actually, which the name is RhinoVolt. Actually, it's totally based on the graphic statics, but actually, Philippe make the 2-dimensional graphic statics to 3-dimensional simulation. Not only he himself, but also his student, Barry, right now working in UPenn. They actually develop different kind of plugin in Rhino for actually to implement the 3-dimensional graphic statics through the computational design process. And I find, I think it's two kinds of approaches, but actually the final result maybe finally have some very similar solution result. But actually, RhinoVolt probably will go to some arch or this kind of vault structure system. It looks like always like this kind of a similar linguistic kinds of form. And at the same time, when we collaborate in the last 5 years with Mike's team, I think it also goes to, from the architect perspective, it also goes to some linguistic problem, because Amoeba, because it's based on the same homogeneous one material compression or tension solution, so which goes to a continued layout of the material, which should be only fabricated by the 3D printing or by the same material, maybe timber, for example. When we go to the real construction scenarios. Normally, we will implement different materials. For example, we use concrete as for compression and use steel for tension. So the question goes to Mike. I want to ask the limitation of amoeba, because we find it's really good for the distribution of one single material or the homogeneous material system. Is there any future possibility you want to develop? Amoeba could make solution of multi-materials or transform this different kind of density of the same material in the fabrication process. Do you think any kind of scenarios or possibilities would you like to develop in the future?
Yes, I can answer that. It's a great question. Amoeba, because it's developed for the general public, so it needs to be foolproof. No matter what mistake you make, it can always run. So that's the requirement for a commercial program, which can be used by many people with very little knowledge about topology of nation. So amoeba is only implement a tiny amount of the research we have done. So the functions inside amoeba is probably 10% of the algorithm we have developed in our research group. So if you look at the publications, many years ago, we have already been able to optimize for multiple materials. In your design, you can have mixture of concrete and steel bars. So we can find those the reinforcement bars patterns in reinforced concrete. We can also optimize for composite structures or optimize for dynamic effects. So these more advanced functions will be gradually implemented into amoeba in the future. At the moment, we have only implemented a very small, very popular functions for the general users. But when we have a specific project, often we use our in-house software tools to tackle the more complicated design projects. So it doesn't mean that BESO can only deal with one homogeneous single material. It can definitely deal with multiple materials, other complexities. Because our method is a post-processing process of whatever you can analyze. So as long as you can analyze, we can read the output and make some judgment to change the current design and make it better.
Very good answer. So we're looking forward.
Can I just?
Yeah, please.
I just add to that because I remember a time when Mike we were collaborating on other projects, and we had a project that required very unusual tensegrity arrangement. And we said to Mike, what software do you use for tensegrity? And he said, well, there isn't any. And that was just before our Easter holidays. And then, as Mike mentioned, we had these Monday meetings. And the next Monday we met, literally just a few days later. And Mike demonstrated a tensegrity software that he had made just over the weekend, the Easter weekend. And that's, compressive. Do you remember that, Mike? I mean, it was, yes, that's obviously yes. Compressive and tension elements in the concept. So the BESO and ESO is just one element of Mike's enormous view of this. And I think the idea of composites and also engineering as a system rather than just a simple monolithic material is a very important one. We don't want to be restricted to that kind of reductionist possibility.
Yeah, I have one more question I want to ask Mark, because we make a lot of discussion for this kind of tool-based. It's like a plug-in culture right now in architecture and structural engineering discipline. Actually, a lot of PhD program and a lot of program developer actually they engage a lot to this kind of developing different kind of softwares as tools to make solution for the both engineer and the design thinking process. I mean, I want to put forward some negative part for this kind of plugin culture, because actually, do you think any limitation or any constraints for us? Because when we implement this kind of new tools, is there any similarity or this kind of linguistic style which can comes out by this kind of plugin, this kind of new tools? Because actually the authorship goes to the developer. Maybe Amoeba have certain kind of authorship. When the architects implement this kind of tools, you can very easily figure out this kind of certain stylistic aspects of the tools. So actually in the future, if you use this kind of plugin tools, it will easily figure out which part you collaborate. So authorship actually is not both on the architect and the plugin developer. So the question goes to Mark Burry. So would you like to give us some comments or your thinking on this kind of new authorship in both architecture and the structural engineer academic culture? What will happen and what's the limitation? What's the positive and the negative part of this kind of culture? Would you like to make some comments on that?
Yeah, so the term I've written about a lot about this is what I call the enfranchisement of the amateur. So you give these very sophisticated tools to people with very little talent and they produce something that looks credible. So what? So my answer to your question very simply is a piano. So a piano is basically an algorithm. The input is my force and the output is the sound. Now, anybody can go to the piano and apply the algorithm. They can put their fingers on the keys and it will make some sounds. Some people are gifted. They can take an interpretation of someone else's music and play it. But there's another person who actually comes up with the music in the first place. And it's funny you should ask this question because I'm writing a paper at the moment called A Blank Piece of Paper. And so the answer to your question is really, if you have to rely on the plugin or the algorithm, it means you don't have any skills in creating the narrative. And I think that there's always going to be room for the person to somebody always has to come up with an idea and then extend that idea through a narrative. And the richer the team in terms of talent, the better that narrative will be played out. But the narrative won't come from AI. The narrative won't come from plugins. It'll come from the human spirit and the talent to make that spirit into music.
Very good answer. I think it's a question I was also asked by my student and also sometime by my friends. But I think Mark today gave a very good example, piano music. I think it's a great answer to all the audience today, because probably they want to ask the same question, similar question I've put forward. So I think we probably have one more opportunity. And I want to check from the audience, is there any question would like to put forward to Mark and Mike? Or Xiang, would you like to have one more question for the last 5 minutes?
Actually, I still have a questions, which is I want to ask Professor Mark Burry. The thing is about the target of the optimization, because when we do the structural optimization like we have used, the target is to in most of the time is to reduce the amount of materials. But if we are doing new fabrication techniques like the carving of stones, and by the prefabrication process, there is a lot of waste of the materials. And how do you think of these questions? Do we really reduce the use of the amount of materials, or there is still some waste, or there is still some new possibilities to for us to research and do and try some new design method, or create new fabrication techniques?
So I will pass this over to Mike after I've given my answer. So the irony of optimization is that we zero in on the minimum amount of material, but it won't necessarily be the efficient way to make it. So obviously, if we're using additive techniques, that's not too bad, because what I love about Mike's presentation today was the fact that you can get different answers with similar performance. So it's not like you zero down to the answer. It is the architect's way. It is finding options that are all viable. Now, I think the viability obviously is going to be conditioned by an aesthetic sense, but it'll also be conditioned by its buildability. But it's a fundamental irony that I can't answer, that the better we get at optimizing, the greater the challenge we have to the builder. Sure, less materials, but it might be a lot longer to make it. But I think Mike will probably have some thoughts on that too, because you've obviously put a lot of work into looking for options and not just the answer.
Yeah, I think these kind of tools only give us some initial ideas. And the fact that now we can find many different design forms. And from these forms, we still need to simplify and rationalize in order to make it, can make them to be practically realizable, and also to save the construction cost. We can't simply take what comes out of Amoeba and try to make them straight away. There's a lot of creativity and intuition after we got those initial concepts from the tools like Amoeba.
Very good. So I think probably we need to finish this session, because New will follow by another workshop in several minutes later. So tonight is a great honor. It's a fabulous 2 lectures and talks between 2 masters, Mike Xie and Mark Burry. I think both of them play a leader roles, the leadership globally, not only in the discipline of architecture, but also the structural engineer and robotic fabrication and so on. I think I would like to great thanks to Mark and Mike, because thanks for your support to DigitalFUTURES. I think the culture, actually the sharing culture in DigitalFUTURES actually is learning from your generation, because you really make a lot of contribution to the discipline, to the pedagogy. At the same time, especially Mark Burry actually last year gave a lot of advice to the PhD program. I'm looking forward in the future, both of you can give a lot of support to the international collaboration and to the PhD program. At the same time, to the new knowledge platform, DigitalFUTURES, we need your support. And I think the audience is from a lot of students globally, not only China, but also the other countries. So the 2 fabulous lectures give us a fantastic experience to learning not only architecture design, but at the same time, the structural engineer is also kind of art. So I think what's Mike doing is really kind of art. We year by year find a lot of potential beauty, which we could find from the Amoeba. So it's kind of very fundamental methodology. And actually in the future, we're looking forward to learning more from Mike and have more collaboration with both of you. So thank you so much tonight.
Thank you.
Stay with us. It's really late. I think around 12 o'clock in Melbourne.
Good night.
So thank you so much. So I would like to say bye-bye. In Saturday, I think we'll have a closing ceremony. Thank you so much. Bye-bye.
Thank you. Bye.
Thank you so much for the invitation. Bye. Bye.
Bye.